This is lesson 3 of unit 7, separation of variables. We're going to start by finding general solutions of differential equations using the separation of variables. Now, we've done this without formally introducing it in earlier sections, so now we're going to do it more formally. So what we're looking at is a differential equation that is in the form of f of x times g of y. So what we want to do is separate the x and y's to both sides of the equation so we can integrate them separately and then solve for y so we have a solution in the form of y equals h of x. So for number 1, what we're going to do is we're going to move the y to the left-hand side and move the dx to the right-hand side by cross-multiplying. So we are going to have well, let's put the y first. So we're going to have y dy is going to equal 2x dx. Now what we're going to do is we're going to integrate both sides, the left side with respect to y and the right side with respect to x. So we get 1/2 y squared equals x squared, and then we're going to have plus a constant. Then we're going to multiply both sides by 2 to get rid of the 1/2. So we are going to have y squared equals 2x squared plus, and you can call this a different constant if you want. And then you can leave it this way and write it as 2x squared plus y squared equals c1, or you can go ahead and solve it for y, and so we'll get y equals plus or minus the square root of 2x squared plus c1. Either form is acceptable. Okay, letter B is the same type of problem, so I am going to leave that for you guys to do, and then I will write the solution here. Same with letter C. So I'll put the answers for both of those. Pause the video at this point, work them out, and then check your answers. Okay, now, with regards to letter C, I want to point out something. A lot of you might not have this answer. You might have an answer that looks more like this, that you have e to the 1/2 x squared and you have a plus c up here. Remember that this can be written using our law of exponents as e to the 1/2 x squared times e to the c. And this is just a constant that we can call c. So that's why we can write it, our k, as I called it here, because I didn't want to have too many c's. So this is going to be k. So that's why you get this answer. And we'll talk more about that in the next section when we talk about exponential solutions. Okay, so then for letter D, this one is a little different because we have some different types of functions going on here. So let's go through that one. So we have a 4y prime minus 3x squared equals 0. So the first thing we'll do is we'll write it as 4y dy dx, which is y prime, equals 3x. So now we can write this as 4y dy equals 3x dx. And we're going to integrate on both sides, on the left with respect to y and on the right with respect to x. And now it becomes more like the one we did in letter A. So we have 2y squared equals 3/2 x squared plus c. And then it's just a matter of dividing both sides by, dividing both sides by, oh, I wrote the wrong equation down. I'm sorry. This shouldn't be 3x. This should be 3e to the x. 3e to the x, 3e to the x. So this will be 3e to the x plus c. Sorry about that. And now we're going to divide both sides by 2. So we'll have y squared equals 3/2 e to the x plus c. And again, you're going to take the square root, so you get y equals plus or minus the square root of 3/2 e to the x plus c. And again, that should probably be c1. Not that it really matters, because it's still a constant, but if you want to differentiate it from the other constant. Okay, so then example 2 is the same type of problem. So again, I am going to let you guys work that one out, and then you can check your answer. So pause the video at this point. Okay, and there's the answer to example 2. And if you do have any questions, you can ask them in class. Now the next example talks about finding a particular solution. So in other words, how do we find the value for C? And this isn't any different than how we found particular solutions of any integration problem we did in Unit 6. So we're going to start by solving the differential equation, and then we will apply the given condition to solve for solve for C. So again, we'll separate our variables. So when we do that, we get x dx equals, and when we move that to the other side, it'll become e to the positive t, and then we have dt. So then we're going to integrate both sides with respect to x on the left and t on the right. So we are going to get that we have 1/2 x squared equals e to the t plus c. So now right here, before you do any square roots or anything, we have our general solution pretty much right here. I think it's easier to find c at this point instead of solving all the way for x, because then we're dealing with square roots, and then we can put it back in and then solve for x and have the square root and everything. So I'm just going to substitute right here. So I'm going to do, I have that t equals 0, and this will be x. So I'm going to put 1/2 of 1 squared equals e to the 0 plus c. So I have 1/2 equals 1 plus c. So c will equal -1/2. So now what I can do is I can take my general solution and I can finish solving for x. So that just requires multiplying both sides by 2. And then taking the square root of both sides. And that is our particular solution. And these are terminologies you need to be familiar with. All right, next problem is the same kind of problems. The next two are, so I'm going to leave those for you two, these two for you to do, and let me write the answers here. Okay, I'm going to show you example 5 solution first because I want to comment. It's probably more likely if you see this solution that it would be in the first form, because the second form seems a little awkward. But if you solved it for y, you would have to have, actually you don't need the plus or minus there. You would have to have the cube root of 9 minus x to the 3/2 squared. So that means that your c is equal to 9. That's what you should have gotten. So again, that is probably the preferred form. Now to show you the solution to number 4, you want to remember to mark that x and y cannot equal 0. That's important because of the original conditions, and also especially for x because you can't take the natural log of 0, but it's squared, so you don't have to worry about negative numbers, but you do have to exclude 0. But 0 for both x and y are excluded from the original differential equation. Okay, now the last part of this has to do with those exponential models, and it refers back to what we did for number 1, part C, and how we came up with that general solution. So these are on the AP test quite a bit, and what you want to look for, so you can skip through the idea of finding the differential equation, but if you do have to go through it, it's still, you'll know what you're looking for. You want to, growth and decay models are where the rate of change of some quantity y is directly, and that's important, directly proportional to itself. So the differential equation will have that form. And if that's the case, here's what happens. This is called the law of exponential change. If y is a differentiable function of t such that y is greater than 0, and y changes at a rate proportional to the amount present, so that was our differential equation above, dy dt equals kt, then the general form of the equation will look like y equals c e to the kt. C is the initial value, so that's what happens when t equals 0, y will equal c. And k is considered the constant of proportionality. So you want to remember, when k is positive, you have growth, and when k is negative, you have decay, which is what we learned in Algebra 1. Okay, so we're supposed to prove that this model supports it, and we kind of went through it a little bit with that one example problem. But I didn't do it with you, so let's go through and do it now. So we're going to start out with dy dt equals kt. And then we're going to solve this differential equation. So we're going to have dy over y is going to equal k dt. And again, we're going to differentiate both sides on the left with respect to y and on the right with respect to t. So when we find the antiderivative of 1 over y, we end up with the natural log of the absolute value of y, and that's going to equal k times t plus some constant. Now, to get rid of the natural log, because I want to solve for y, is I am going to raise both sides to the power of e. And when I do that, since natural log and e are inverses of each other, I will be left with y. And then I'm going to have e to the kt plus c. Now here is where I'm going to go ahead and write e to the kt times e to the c. And I am going to let e to the c equal capital C. So my differential equation solution becomes capital C times e to the kt. And that's what I was implying on that last example from number 1, that's what we have here. Okay, so let's finish up this lesson with doing a couple of examples using this model. Example 2 says the rate of change of y is proportional to y. When t equals 0, y equals 3, and when t equals 2, y equals 6. The reason why we need two conditions is because we have two constants. We have the constant of proportionality, which is k, and we also have our initial condition, c. And the nice thing is we're given the initial condition, so we already know that c equals 3. So we're good with that. So we want to then solve it once we find k for when t equals 3. So let's set up our differential equation. So we have dy dt equals ky. So I'm just going to go ahead and write that y is equal to ce to the kt. And you can do that. The assumption is that you recognize this relationship and you don't have to go through the steps for solving it. So we already know that c is 3, but if you wanted to prove that, if you're asked to do that, you can write, so we know the initial condition is 3, so we can write 3 equals c times e to the k times 0. So we have c equals 3. So we have that much. So here's where we're at now. We have our model, which is so far y equals 3e to the kt. And now we have to solve for k. So we use our other condition. So we're told that when t equals 2, y equals 6. So we are going to substitute that in the equation and solve for k. So 6 is going to equal 3 times e to the 2k. And so we have 2 equals e to the 2k. Take the natural log of both sides. So we're going to have ln of 2 equals 2k. So k is going to equal ln of 2 over 2. So k is approximately equal to 0.347. So now we have a real model here. So here is our model, our complete model that we can use. So we have y equals 3e to the 0.347t. Now we want to know what happens when t equals 3. So we're going to substitute 3 in our model. And Obviously, you have a calculator for this, and you would get 8.46. Whoops. Sorry, can't read my own numbers. I'm writing them down in the wrong order. 8.486. Okay? And one more problem. You guys go ahead and do this one. Well, you know what? I'll do this one because it's a little different. It's not a direct proportion. We're told the growing rate. So we're going to have to solve this differential equation. So because it doesn't say it varies directly, what it gives us is the way it varies. So we have to set up this differential equation and solve it. So we're going to do dB is going to equal 3,000, and I'm going to integrate both sides, e to the 2t over 5. And integrating both sides, I get b of t, if you want to call it that, is equal to 3,000 times 5 halves e to the 2t over 5. If you're not sure where I got the 5 halves, you might want to here let that equal u, and then do your du. So you get 2/5 dt, so dt will be 5 halves du. So that's where that comes from. Okay, and then of course we have our plus c. Okay, and then simplifying, so we have b of t is equal to 7,500 e to the 2t over 5 plus c. And then at t0, we're told there were 7,500 bacteria present, which we already figured out from just doing the problem. And then we want to know what happens when t is 5. So we just have to find b of 5. And what we're going to understand here is that, and I forgot to mention this, that this c is going to equal 0 because we have a rate and we're told how many bacteria are at the initial value. So that c does not come into play because it becomes an exponential model like that. So we're going to get c, that c equals 0. All right, and now just finishing this up, we're doing 7,500 times e to the second power. So this is equal to 55,418 bacteria. Okay, and that's, oh, there is one more. I thought that was the last example. We have 2 more. Okay, so let's go ahead. These 2 I will let you guys do, and I'll write the answers here, and then you can check them, and we can go over them in class. All right, here's the answer for number 4. There's the model, and then here is the expected revenue, and this is what happens. 2013 would be a T of 5, because that's the difference between 2008 and 2013. Okay, now then when I went to write the answer for number 5, for example 5, I realized that this was a problem, it was a little different, because this is where we have a direct proportionality, but we also have to find C and K, and we haven't done that yet. C had been given to us in the other example. So let's go ahead and do this one together as well. Suppose a population of insects increases according to the law of exponential growth. So that right away is going to tell us that we're looking at CE to the KT. There are 130 insects after the 3rd day of the experiment, and then 380 after the 7th day. So that's, again, I said this earlier, why we need 2 pieces of information, because we have 2 constants we have to find. So we're actually asked to find what was the initial population, or our capital C. So we know our model is going to look like this. Y equals CE to the KT. So we can go ahead and use those 2 conditions to write 2 equations and solve a system of equations. So the first condition we're given is that there are 130 insects on the 3rd day. So that would be E to the 3t. And then we're also told that there are 380 insects after the 7th day. So that would be CE to the 7T. Oh, I'm sorry. These should be Ks because we're substituting for T, not K. So this is K, this is K. Now, what we can write here is we can do a couple of things here. We can solve for K first by making a ratio of these two. So we can do 380 divided by 130 is equal to CE to the 7K over CE to the 3K. And I usually do it this way so that my exponent will be positive. So what I get then is these will cancel, and I'll have 338 over 13 equals E to the 4K. Now this becomes pretty simple to solve them. So I'm going to take the natural log of both sides. So the natural log of 38 over 13 is going to equal 4K. So K, if I divide this by 4 as well, I get that K is going to equal 0.262. And then what I can do then is I can put that in either equation and solve for C. So what I'm going to do is I'm going to take the first one here, and I'm going to write that 130 divided by E to the 3K equals C. So I'll just substitute in for K. And you could have done it with the other relationship too. So this is 3 times 0.262. And when you do that, this will be C. C is going to equal, you get a decimal, but you want to round it. So you had 58 insects initially. I'm having trouble spelling insects. There we go. And now we're done with lesson 7-3.